Hello. In this video, I'm going to be talking about my final project for fuzzing seminar, which I'm calling Scoute and Route. At a high level, this is a target-assisted extension to regular coverage-driven fuzzing, mutation fuzzing. And it's based on the idea that when a fuzzing target rejects a certain input, you can look into the exact condition that blocked progress and then also what would have satisfied that condition. And then the fuzzer ideally can use that information in two steps. The first being by probing whether useful coverage is hidden behind the blocked condition, and the second being by trying to repair the input so that it reaches that coverage normally. I'll start by motivating the problem. So in general, coverage-guided mutation fuzzing works quite well when a small byte edit or a small mutation can satisfy a branch condition. But for structured file parsers like the one on screen right now, which is a PDF object stream, a lot of the time there are several related fields that all need to be valid at the same time. So on screen there's a type field, numeric metadata, and a payload layout. And it's not enough if just the fuzzer is able to correct the type field to be a object stream token. It then also needs to have the right numeric metadata and payload layout so that they're all coherent with one another. And then finally it can pass this conditional where it checks whether there's a valid decoded payload. And after this conditioner, there might be many edges that the fuzzer would otherwise really want to find to increase coverage. But if it's behind this structured parser conditional, then it's very unlikely to be able to get past it. So this creates two big problems for the fuzzer. First, there might be many blocked conditions or parser conditions that it could try to cross, but the coverage alone so far doesn't say which one is worth the effort, because by definition those parts of the code haven't been seen yet or covered yet. And then the second issue is that even if it chooses a useful blocked condition, the repair, as in how it needs to modify the seed to actually get past that condition, has to be coherent enough to actually get through. So Scoute and Route tries to split these two problems apart, where the Scoute part estimates which blocked conditions are actually promising and maybe worth the effort to try to get past, and then Route tries to make that condition reachable. So I designed the project after reading some of the XPDF source and trying to figure out where coverage was stalling during phase 1. And the two patterns that I saw show up a lot are like a text pipeline where the PDF tries to extract text, and the other is stream bundles. And they're both similar, where as an example, the text pipeline usually has to bundle a page object, a resources dictionary, a font entry, a usable font object, and then that all needs to be used correctly by a content stream. And you can imagine that for all of these to line up perfectly is very rare, and that's why the fuzzer has a hard time getting past these conditionals. And stream bundle is very similar in the sense that it also needs to have all of these different fields be coherent, but there are certain differences in the nature of some of these stream bundle tokens that require certain slightly different strategies. So these are really the two patterns that motivated the design, and in the hopes that it would help me get better coverage on XPDF, I kind of made these their own micro benchmarks or like micro targets, and I tried to show in the evaluation eventually that the strategy achieves higher edge coverage on these two micro benchmarks. I made this little animation to try to show the idea abstractly. So the purple dotted region is the coverage the fuzzer can currently reach, and then I have these regions labeled A and B that are both unseen because each is protected by a blocked parser condition, which is this orange line. And at this point, the fuzzer doesn't know which of these frontiers is worth trying to cross because it doesn't know whether A or B is the better next target. So if repair attempts or attempts to get past these blocked parser conditions are expensive or unreliable, choosing the wrong one can waste a lot of fuzzer effort. So the first part of Scout and Route is a triage question. Before committing to a real input edit, the fuzzer wants to ask, if I could cross this blocked condition, how much unseen coverage would be behind it? And that's the whole point of the Scoute probe. Here, the Scoute probes both candidate regions. So conceptually, it forces each blocked condition and observes how much unseen coverage lies behind it. And this is only a temporary probe. It doesn't actually count the edges it finds as true edges, because it essentially just forced the conditional to be true. But it's still able to estimate the promise of crossing each parser condition this way. You can see that after scouting, the difference between A and B is visible. Like, the fuzzer can realize that A is small, so there's not much hidden coverage, and therefore it shouldn't waste the effort of actually trying to route to A. But the Scout for region B is able to see that it's much more promising and that there are a lot of edges waiting to be covered if only the reachable coverage were able to expand past that barrier. So that's the main purpose of Scout. It's to find these blocked regions and also to prioritize which blocked region out of many is worth attempting to route. So once the Scout step has finished comparing the options, the fuzzer chooses the most promising frontier, and in this case it chooses B. And at this point the question changes, because the fuzzer has already found a promising frontier, but it still needs to make that frontier reachable by a normal execution, or in other words, like, it needs to find a seed that can actually get there. And this is where the routing step comes in, since route tries to connect the chosen frontier back to the current reachable region. And in concrete terms, it applies an input repair that's supposed to satisfy the blocked parser condition without forcing it to be true. And if the repair is good enough, normal execution should cross into the region that Scoute identified. You can see that now the purple region includes B, and the fuzzer can now fully expand into all of these edges that were hidden in B now that it's successfully routed past that block. So that's essentially it at the conceptual level. The Scoute chooses a promising frontier, and then Route tries to convert it into actual coverage. And the actual fuzzer loop implements this with a target side runtime, a Scoute execution, a promise check, and then a normal routed execution. So this diagram pretty much shows the whole idea, the whole loop. And you can see that the top row is just a normal fuzzer where there's a seed corpus that gets mutated, and then whenever there's a seed that actually adds coverage, it will store this into the seed corpus. But now there's an additional path where when a seed doesn't end up generating new coverage, it records the ID of the conditional that it got blocked by, and then also a hint. And a hint can be, as an example, just like the bytes that maybe if placed correctly within the seed, it would be able to get past that conditional. And then it will do a Scoute probe. So it will jump past that conditional and then check how much coverage is beyond that conditional. And if it is like fruitful, if there's a lot of edges there, then it's going to try to route this back to a seed. It's going to try to reach past that conditional, and then finally it will test whether that actually uncovered edges. If it did, it'll add it to the seed corpus. Otherwise, it will just discard this routed seed. So the full implementation really just needs these three pieces. It's a regular mutation fuzzer, and then a target runtime that can actually report and force these conditionals, so like force these frontiers, and then finally route transformations or route transforms that are able to turn the hints into concrete edits to the inputs, and doing this will hopefully yield new seeds and more coverage. I implemented this design on the fork server based mutation fuzzer that we built for Objective 10, and on the fuzzer side I added all the logic I mentioned on the previous slide, so the Scoute logic, this promise measurement, so edges after you've forced a frontier, and then also these route transforms. I also added a small runtime that can emit these frontier IDs and emit route hints, and then all of the code to force one selected frontier during Scoute mode. And then for the real target, I instrumented XPDF 4.06. The target side can tell the fuzzer what specifically failed, but it doesn't automatically fix the input. So that's really the point of the route transforms, because that's the part that actually tries to turn a hint into a usable repair. And when I was implementing the route transforms, I try to keep them intentionally simple so that they're all cheap to run and they're all local repairs, because it kind of defeats the purpose if the process of repairing is just brute forcing anyway. So I try to keep it to ones that it can either succeed quickly or it can just bail on that frontier. And sometimes the repair is to just replace a wrong value with the hinted one. So it can just kind of look for the wrong value and substitute those occurrences, or sometimes it needs to repair an existing field before inserting a duplicate key, because parser semantics can make it so that duplicates are ineffective. Like if you have an insertion of a particular byte that's later in the input, then it could be useless because really the first occurrence or the byte that's in an earlier position will have already determined the control flow. So sometimes it's inserting a missing field, other times it's replacing an existing field, but I also implemented some small multi-step recipes that can try to chain a few of these together. What I was finding was a lot of the time you would need to have multiple of these steps in succession, or else it will kind of bail too early because it kind of gets through a conditional and then there's just no edges, there's another conditional. So if you can just link together a few of these, then a lot of the time you can make your way all the way into a region with lots of near edges. So the main question was to see whether these repairs were enough, and I tested that in two stages. First on the small micro targets I mentioned earlier, and then the other on the actual full XPDF. So the way I measured these three targets is by doing paired trials against a baseline, and the baseline in this case is the same fuzzer with all of the scout and route logic disabled, and I made them paired trials so that the baseline and candidate, the candidate being scout and route, start from the same random state and the same seed pool. And I report final edge coverage, coverage area under the curve, and throughput. So these were the results I got on the 2 micro benchmarks. You can see that in both cases, scout and route was able to increase the edge coverage. For stream bundle specifically, was able to do so significantly over the baseline, and that was a really good result. But at least it shows that for these controlled targets, it can work, at least when the barrier shape matches what the routing step can actually repair. But I did also try to answer the harder question, which is whether that transfers to the real full XPDF parser. And unfortunately, I didn't end up seeing any benefit on the actual XPDF runs that I did. And you can see that it's like pretty much statistically indistinguishable from the baseline. Pretty like on average only differed by 4 edges. And the area under the curve is also slightly negative. So the bar graph on the right explains what's happening to some degree. You can see that the mechanism is working. Like the scouts are firing, and then many scouts end up actually having edit attempts, and therefore they're trying to route, but then there's this huge drop off from edit attempts to actual new coverage. And that's like a interesting effect that I didn't see as much in the micro targets, but essentially the edit step isn't powerful enough to turn most of them into actual durable progress. But just looking at these results, there's still some ambiguity, because it could be that the Scoute step is picking bad trigger points, or it could be that Scoute is picking useful trigger points, but the edit step can't actually build the right inputs from those trigger points. So I did another experiment to try to separate those possibilities a little bit. So to figure out which of these two is the dominant effect, I did a controlled experiment where I created a version of Scout and Route that has access to known good quality seeds. And this isn't strictly fair because the baseline wasn't given access to this, but the point of this was to see whether it is the fault of a failure of the Scouts to find a useful signal, or whether the failure is that the edits are too weak to reconstruct the actual repairs that would allow routing to happen. And the fact that this does so well compared to the baseline is evidence that the Scout part is working fine, but essentially the routing transformations are too weak to actually fix the seeds. Either the routing is too weak, or the hints are too weak, or some combination thereof. So unfortunately, that's why XPDF doesn't show very good results. So putting the results together, I don't think the story is necessarily that target hinted scouting is useless, because we've seen that the Scout can point at useful regions, and that the full Scout and Route mechanism works quite well on the source grounded micro targets that I made. But on real XPDF, the bottleneck is this like editing / routing stage, and real parser bearers often require a bundle of related fields to agree. So the local edits that I implemented, which pretty much only can repair one piece at a time, still continued to struggle. So the natural next steps from here would be to have a richer target side context, essentially having more and better hints, and then have a smarter way to bundle repairs together so that it's able to actually successfully coordinate several of these changes at once. And then also I think it'd be useful to have actual like route feasibility scoring, because right now it just really looks at the promise in terms of the number of edges beyond conditional, but it should also weigh how difficult it's likely to be to actually access those rewards. And I think either way, it's a good launching off point, and I think eventually it might be able to actually show a good signal in XPDF.